look like I'm doing? I'm going to the moon.
Are you actually trying to make a rocket?
That's correct.
You know those aren't real fins, right?
How would you know?
I majored in rocket science at MIT. What do you mean, how would I know?
Do you have a fin on you?
I do. This aluminum, titanium, carbon fiber build has a curved shape. This allows for less drag on the rocket and also creates more lift, thus increasing the maximum height that can be achieved by said rocket. So, as you can see, there is a right angle on this fin. With the reasons I've given you before, this fin would be ideal for your purposes. Even though it's been proven that the shape of the fin doesn't matter as much, that cardboard nonsense will not get you anywhere.
You know what? I'll be right back.
Oh, okay.
Yo, just graduated from Harvard.
I just forgot everything. Oh, what
You
hit
know
me?
what? I think I have a solution.
Oh, I got hit. I'm down.
Get up. Come on, I didn't hit you that hard.
I did. I felt it. Nice nose cone.
Okay. Let me explain something to you. The first thing the air touches on a rocket as it's in the air is its nose cone. So the nose cone is one of the key parts that maintains stability for the rocket, alright? So if you want to use this, you're going to go about 2 feet into the air and then everything's going to blow up. Although, I have a solution for you. Aha! So here's an ideal nose cone for your setup. One of the key factors that affects drag in a rocket, which would significantly lower its maximum height, would be the diameter of the nose cone and the speed of the rocket. The speed of the rocket is also affected by the nose cone. So, you may be wondering, why is this curved? Wouldn't it be more ideal if it was a sharp pointed object at the end so it would cut through the air? Unfortunately, that would make sense, but a rocket doesn't go straight up into the air. Rather, it would turn after a certain point. It's a parabolic shape. So, with a point, as it keeps turning, it would have significant amount of wind and air pushing against the point from either direction, and the point would most likely wobble and break off. And your rocket's done for. Although, having a cone shape like this does have its downsides. One of the downsides is that it'll have to push more air as it comes down onto either side. So the larger the diameter is of the cone, the more air it'll have to push out. So there'll be more drag and more resistance from the air that is pushing out, thus decreasing the maximum height. But it will still yield better results than if it was a complete straight pinpoint, since it would still break off. Alright, does that answer your question? So basically, you just want to make sure the diameter of this is not too wide, but just wide enough to keep this rocket stable.
What question? I didn't ask a question.
Fabulous. Let's strap this on, get to work. What are you doing?
What does it look like I'm doing?
Ah, structuring the cone of your rocket, huh?
Good man.
Alright, well, I have a suggestion to make.
Yeah.
I brought you this. See, the problem with yours was that it had many pieces sticking out of it, and that would have increased drag by a significant amount. Here, this structure is very streamlined, so the air will simply pass over it, not decreasing drag by very much at all. So the thing with these kinds of cylinders is that the wider they are, the increasing diameter, the more drag you're gonna have. So that piece over there was way too large for your purpose. This adequately covers everything you need. There you go. Catch you later. What are you up to now?
You know, just trying to make it symmetrical.
I have a solution for you. I don't know, I forget where I learned it, but there's this thing called a midpoint formula that you can incorporate. As you can see, the distance of the top of this car lengthwise is 1, 2, 3, 4 meters or miles, I forget. Just pretend this is a nice coordinate plane. Bam, bam, boom, blow. You got yourself the midpoint, which would be 7 over here. You align it to that. Give it a little bit of tuck it in place. This baby is ready to fly.
What is the midpoint formula?
Actually, I'll tell you, would be x1 plus x2 all over 2, comma, y1 plus y2 all over 2.
Where did you learn this?
I forget, it's like some class.
I wish I took that class. It sounds like a great class.
It sure
with
was.
a great teacher. Hey you, I'm tired of your intelligence. Hey you get up. I just graduated from CIT.
I forgot everything.
It's okay, I know everything again.
Will you teach me?
Maybe.
Alright.
Well, as you can see by this rocket, it has a form of symmetry. If you were to draw a line right down the middle of it, you can see that this part of the rocket is a reflection of that part of the rocket. However, that isn't enough. You also need rotational symmetry. This is important because it gives more balance, which makes the rocket less prone to wind resistance.
'Cause I can fly,